Friday we defined a new term. We called it centrifugal force as opposed to centripetal force, right? Centrifugal with an F versus centripetal with a P. Centripetal force, you remember, was that force that acts toward the center of a circle when an object is going around in a circle. The centrifugal force is that outward force. And we said on Friday that the quotation marks are really in the wrong place. It should be around force as opposed to the word centrifugal. The reason it should be around force is because it's not real. It's not a real force. It's an outward something, but it's not an outward force. What really is it that makes us feel as if we're being pushed to the outside of a circle when we're going around in that uniform circular motion? One word. Not gravity, no. Inertia. Yeah, we want to go in a straight line. If I'm on this merry-go-round, here's the center of the merry-go-round, here's the bar of the merry-go-round. I'm at this spot on that merry-go-round. Okay, this is the outside of the circle of that merry-go-round. As this outside of the circle goes like this, I'm, let's say, in this spot right here, going in a straight line, going like this. What happens eventually? As this spot on the merry-go-round, this bar on the merry-go-round, makes it to out here, I have gone in a straight line to out there. So it makes me feel as if I'm being pushed to the outside. Really, it's me going in a straight line towards the outside. Does that make sense? Centrifugal force is really just inertia. Now, if I happen to be pushed up against the wall on the outside, I really feel like I'm being pushed out against the wall. What is that? What is that? Like, what is that sensation of me being pushed out there against that wall? It's the centripetal force pushing you in, the wall pushing you in. Whenever we have an acceleration inward, we have a fake force or a perceived force outward, right? Centrifugal force, what is it really? Two things. Inertia, if I could spell that. And again, we'll put quotation marks around force. It's really just inertia, and it's the centripetal force of the wall pushing in. Those two things combined give us that perception of the centrifugal force. All right, today we're going to talk about something not new, a little bit more of an application of what we've done with centripetal acceleration, centripetal force. This is going to be a pretty important portion of your field trip that's coming up on May 29th. This is what we call vertical circular motion. On the Mindbender, the world's largest indoor roller coaster, you're going to go around, you're going to go up about 50 meters into the air, then you're going to pretty much free fall, pretty much straight down. You're going to go from 0 to about 100 kilometers per hour in about 2.8 seconds. And then you're going to go around a loop, a vertical upside down loop, and then a little bit later on you're going to go around 2 vertical loops. So there's 3 upside down loops. Okay, this is what we're going to analyze today, these vertical loops, these upside down loops. We can analyze the motion of an object anywhere in that loop. We will choose to analyze the 2 extremes, being the top of the loop and the bottom of the loop. Here's the roller coaster cart at the top of the loop. Here's the roller coaster car at the bottom of the loop. Tell me what forces act on the car and you in the car at the top of the loop. What acts on it? What pushes or pulls on this car? Ben? Gravity. Gravity acts which way? Good. In fact, gravity is going to act down whether you're at the top of the loop or the bottom of the loop, right? Does that make sense? Like, gravity doesn't change between the top of the loop and the bottom of the loop. Okay? One, maybe the slightest little immeasurable bit, right? Like 9.81000000, 9.81000001, right? It's effectively the same value. What else acts at the top of the loop and or the bottom of the loop? Yeah, Demi? Good. There's a normal force. That's the force of the track pushing up, right? Right now, the normal force acting on me is the force of the floor pushing me up. Right now, the normal force on you is the force of your seat pushing up. The normal force of the roller coaster car on the roller coaster car is the force of the track pushing. Now, that normal force, when you're at the bottom of the circle, is acting upward, and its value is bigger than gravity. How do we know that its value is bigger than gravity? Like, why is it necessary to be bigger than gravity? Yeah. If you're moving in a circle, the net force needs to be which way? Not necessarily up, just generally, when you're moving in a circle, the net force needs to be toward the center of the circle. When you're at the bottom of the circle, where is the center? Above you, right? So that normal force has to be bigger, that inward force has to be bigger than that gravity outward force. Otherwise, the net force wouldn't be toward the center, and then you wouldn't move in a circle. So if you want to stay in the circle, the normal force is bigger. If you want to go out of the circle, like it's a roller coaster loop and you're going out like this, well, then maybe the normal force isn't bigger. Okay, but as long as you're in a circle, the normal force has to be bigger. Yep. Good question. Which way is the track pushing on you when you're at the top of the circle? It points inward toward the center of the circle. The normal force pushes down when you're at the top of the circle. Now, how big is that? We don't know. At the top of the circle, it may be bigger than gravity, it may be smaller than gravity, it may be the same value as gravity. At the bottom, we know it's got to be bigger. At the top, we're not sure. Now, does this at all look familiar to you, what we've drawn here? What do we do in a situation like what we have drawn up on the board? That is a free body diagram, right? We've drawn two free body diagrams. And what do we do, William, with a free body diagram? Add them all up. So we would say, in both cases, we would say the net force is equal to the sum of the forces, Fg plus Fn. F net is equal to Fg plus Fn. Now, what was the next step usually in these problems? Think back to last unit, right? We've done this a ton of times. Yes, we'd substitute ma for the net force. But before you write that down, a here is centripetal acceleration. So m times a is m times v squared over r, right? A is v squared over, right? Makes sense? The net force is the centripetal force. So let's sub in, instead of m times a, mv squared over r, which is really ma, but it's just a special kind of a because it's moving in a circle. I'm replacing Fg with m times g. Now notice both of these are exactly the same, right? They can't be the same. Like the analysis of the roller coaster car at the top of the circle has got to be different than the analysis at the bottom of the circle. So what's going to make it different? So far, it should be the same. At this point, what makes the top different than the bottom? Mathematically. Height? I don't even see height anywhere in there. It's a good guess, though. Fn what? The value of Fn? Perhaps. Perhaps. What is it? Speed. We're actually going to assume the same speed. That's not quite true. Okay, at the top of the circle, it'll be moving a little bit slower than the bottom, right? But we're going to assume that it's uniform circular motion, that the speed is the same. Yeah? Yes, good. The signs. It's the signs here. At the top of the circle, I don't know what happened there. At the top of the circle, gravity will be negative. Agree? Gravity is always negative. At the bottom of the circle, it's going to be negative as well. At the top of the circle, which way is the normal force? Down. So it's going to be, Rachel S, that is? It's going to be negative. At the bottom of the circle, Fn is which way? Positive, because it's up. Good. So we got a different sign here, right? That's going to change everything, right? What about centripetal force? At the top of the circle, the centripetal force mv squared over r is? Yeah, when you're at the top of the circle, like centripetal force points toward the center. When you're at the top of the circle, which way is the center from where you are? Down, right? If you're looking at the middle of the circle, you're looking down. Bless you. So the centripetal force would be downward or negative when you're at the top. When you're at the bottom of the circle, I'm right here. The centripetal force is toward the center. Which way is the center? Up. So that's going to be a positive value. Now, just like in the last unit when we were looking at these problems involving multiple forces, remember that you're not going to include signs until you sub in numbers. That's why right now they look exactly the same. The next step, though, would be to sub in numbers. That's why we need to start thinking about what's positive and what's negative. Make sense? Now, we've seen the top and the bottom of the circle. Okay, we could analyze anywhere else on the circle as well. Just understand that we won't, because they're not the extremes. The extremes are the important parts. But you understand that if we had a situation where we were analyzing an object right here, we just say the normal force would act this way, and the force of gravity would act this way, and it would just become a two-dimensional problem instead of a one-dimensional problem, right? Which we know how to deal with. Okay, we can deal with two-dimensional problems. We won't do it in this context because there's no value in it. It's the extremes, the top and the bottom, that we really care about. But we could do the rest if we wanted to or if we needed to. Okay, we're going to do an example here on page 264 that's going to put this into play here, puts this into action. We didn't talk a lot about it kind of leading up to this because, well, the reality is, like, we've done these problems before, right? We did these problems almost all of last unit. They were virtually identical to these ones. Bucket of water with a mass of 1.5 kilograms is spun in a vertical circle. The radius is 0.75 and the speed of the bucket is 3 meters per second. What's the tension in the rope at position C? What did I call that a minute ago? What's the equivalent of the rope tension? The normal force, right? So you want to call it Ft like they do, the tension on the rope, that's fine. You want to call it the normal force, that's fine. I'll call it normal force just to be consistent with what we usually do, okay? At the bottom of the circle, that's where we are here, at position C at the bottom of the circle, we'll say the net force is equal to the sum of the forces. I'm going to call that Fn plus Fg. The net force is also mv squared over r. And Fg is m times g. Now let's start subbing some numbers in here. The bucket of water has a mass of 1.5 kilograms. V is 3 meters per second. Divided by r, 0.75 meters. Fn, sub that in. M is 1.5 times 9.81. Now we've got to worry about signs. Remember we said a minute ago? Don't worry about signs until you put numbers in. Now we got numbers. Gravity, positive or negative? Negative, it's acting down. Top of the circle, bottom of the circle, doesn't matter. Put the negative in front of the 1.5. Put it in front of the 9.81. I don't care. There's got to be a negative somewhere in that term. Ben? Good question. M times v squared over r or m times v squared all over r. Doesn't matter. Doesn't make any difference. It gives you the same thing. What about that centripetal force, mv squared over r? Is that positive or negative? You're at the bottom of the circle. The center of the circle is upward from you. That's a positive value. So let's figure this out now. On our calculators here, we're going to say that, what, 1.5 times 3 squared divided by 0.75. That gives me a centripetal force of 18 over here. 1.5 times 9.81 gives me a value of 14.715. Notice that's a negative value. How come it's negative? Negative 1.5 times 9.81. Take that over to the other side by adding, and Fn becomes equal to 32.715 newtons, which we're going to round to 2 digits, equals 33 newtons. So look, gravity is 14. That's the weight of this bucket. The normal force is 33. In other words, the apparent weight, remember the elevator questions, the apparent weight is normal force? The apparent weight is more than twice as much. So we're saying if you were going around in a circle like that, the G's that you would experience would be 2 point something. You'd be more than twice as heavy. You'd feel more than twice as heavy as you really are. Does that make sense? Listen, this is what you do. This is 3/4 of our last unit. F net is the sum of the forces. Watch out for the positives and negatives. Okay, watch out for little things like forgetting v squared over r, just calling it m times a. Okay, other than that, it's the same as last unit. That's why we haven't spent a ton of time on it here. I'm going to ask you right now to take a look at these two questions on page 264. The reason I'm not asking you to do number 2 is because number 2 asks you to analyze right here, and we said that we're not going to bother doing that. All right?